Hi everyone, welcome to Most Math. Today I'll be demonstrating one of De Morgan's laws for logical propositions and sets. Go ahead and write down a truth table for propositions P and Q. What we want to demonstrate is that not P and Q is the same as not P or not Q. So you can basically distribute the not over the and at the cost of an or. Values that P and Q can have are true, 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 false, false, true, and false, false. Standard way you compute truth tables is look at one side and take the innermost operator and do that first. So we'll do P and Q. P and Q is true if and only if both entries are true. So we have true, false, 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 and the negation of this, of course, is false, true, true, true. We'll call this entry asterisk. Go to the other side. First, we will take the negation of P and Q. So that is false, looking at this column, not that column. False, false, true, true, and then not Q, so not this column. That is false, true, false, true. Now we'll take the or of these two columns. The or is true if and only if one of them is true. So that is false, true, true, true. Call this column star. We compare star to asterisk. False, true, true, true. False, true, true, true. Good to go. So they are the same. We celebrate by writing all truths in the column. If and only if, because if and only if is true, if and only if they're the same. So it's true for sets. An example of this would be P and Q, it's raining or snowing. It's not raining and snowing if and only if it's not raining or it's not snowing, for example. Put in any P and Q. Now let's go ahead and take what we learned and rewrite it in the language of sets, since those are far more frequently used in mathematics in general than abstract logic like this. De Morgan actually wrote down the laws in both forms, so we're going to do that here. Alright, we are going to be showing that A intersect B complement is equal to A complement union B complement, and we'll be using what we just showed, that not P and Q is the same as not P or not Q. Okay, notice this is also true if you replace the ands with the ors. It's just proved the same way, so we're not going to be showing that here. Same thing with the unions replaced with the intersects. So we have the intersect, the union, and the complement operators here, of course, pretty standard. All you have to do is translate this into a language of sets. So to show that two sets are equal, you must first show that one side is a subset of the other, both of them. So this is a subset of this, and this is a subset of this. We'll go left to right first. We're going to let X be an element of A intersect B complement. This means that X is not an element of A intersect B. Sorry, the complement goes out here. A is not an element of this. This means that the negation of this statement is true. X is in A and X is in B. It's not in that. So we'll go ahead and apply De Morgan's law here. This tells us that we're going from left to right. X is not an element of A, or X is not an element of B. Which tells us that X is in A prime union B prime. And that's all we have to do to show that this is a subset of this. Alright, let's do the other one. We're going to let X be an element of A prime union B prime. This tells us that X is not in A, or X is not in B. Now we can apply De Morgan's law right away. From right to left tells us that the negation of this sentence is true. X is in A or X is in B. No, sorry, we had or. It switches to and at the cost of a not. Which tells us that X is an element of A intersects B complement. So we've shown that this is a subset of this, and this is a subset of this. So therefore, the sets must be equal. And this is how De Morgan's laws are typically used in mathematics. It's one of the most fundamental things you can do in these kind of contexts. And if you enjoyed this, want to see more math, feel free to subscribe to our channel, and I'll see you next time.